Okay. So welcome to the Institute of Astrophysics seminar series. Today we are very happy to have with us Jorge Gonzalez Lopez. Jorge got his PhD. I think it was a joint PhD, no, between Universidad Pontificia Católica de Chile.
Yes.
O Pontificia Universidad Católica de Chile and the University of Heidelberg. After that, he made his first postdoc at there in Universidad Católica. And then he moved to Universidad Diego Portales, where I had the pleasure of meeting and knowing him in person. And after that, he moved to as a postdoc, as a long-term postdoc at Las Campanas Observatory in Chile. And recently, as a matter of weeks, maybe?
Or weeks, yes.
Weeks. He will become officially, maybe when signed the papers in a few days, a professor at Universidad Católica.
Yes.
So that's very good news to have him permanently as a professor. So today he is going to talk about characterizing the cold interstellar medium of low mass star-forming galaxies as cosmic noon with ALMA, which is one of his many projects ongoing.
Yes.
Actually, from this one I don't know that much. So I'm very
actually that was one of the reasons that you heard my talk about the C+ halos and everything. So this is the other science that we are doing.
Excellent. So whenever you're ready, take that one.
So thank you, Tanya, for the introduction, and thank you for everyone for the invitation to give this talk. So in this talk, I'm going to present work done within the ARCTOMO collaboration. This is a group that we have in Chile that use gravitational lens galaxies to study the CGM of foreground galaxies. I'm going to talk a little about that. And this is work that I have been doing together with two students, Manuel Solimano, a PhD student at UDP, and Victoria Catán, a new master student at Católica. So as an introduction, I need to show a very nice and beautiful picture of a galaxy. This is a local galaxy. This is a spiral galaxy that at the end, we want to study galaxies because these are the building blocks of the universe. Most of the processes that we are interested in astronomy happen within a galaxy. We have star formation, supernovas, AGNs, everything happens in a galaxy. And it's really important to understand what is happening with this galaxy, for example, with this spiral galaxy that is very similar in properties to the Milky Way. So how does it, what is the evolution process for this galaxy? How it came to be the way that it is? So to do that, we need to study different components of the galaxy. For example, we can go and study the stars that we can see in this galaxy. We have blue stars, which are young, massive stars. We have other in the center, another population, where also we could have, for example, in this specific galaxy, there is a starburst going on in the center. We can see, for example, dust lanes that they are correlated with the locations of the new stars that are being formed. But this is only a fraction of what you can see of the main components of a galaxy. If you really want to understand what is happening, you need to go into the ISM and get the information from the gas. For example, now with MUSE, we can study the ionized gas, for example, and we can pinpoint the regions where the star formation is happening. And if you go to ALMA, you can do the same with the molecular gas, which at the end is the fuel for star formation. So if you really want to understand what is happening in a galaxy, in its evolutionary path, it's good to have a view of all the different components. And just to to go back to analogy of the Milky Way, this is a galaxy that is very similar to the Milky Way, a similar mass. And for the Milky Way, if you really want to understand what happened in the past, you can study, for example, all these accreted galaxies and the merger processes that happened in the past. And what is important is that a lot of that activity, specifically for the Milky Way, happened between redshift 1 and 3, which is the epoch of the universe where we have the cosmic noon, when the star formation rate density, the cosmic star formation rate density, was at its peak. So we had a lot of activity. So we know that most of the local galaxies that we see, they had a lot of processes happening in this period of the universe, and it's a good epoch to study, to understand what are these processes, to see them live, or how they are happening in real time. And specifically, the question that I wanted to answer within this project is, what is the molecular gas budget, and if we can, the distribution of normal galaxies at cosmic noon? And by normal, I'm talking about galaxies in the main sequence, but also more abundant and more common galaxies, kind of dwarf galaxies, not the typical massive galaxies that you study at high redshift. So what do we know about the molecular gas at cosmic noon? This is something that is not new. There has been a lot of effort to measure the molecular gas using different tracers at cosmic noon at the redshift between 1 and 3. And for example, I really like this to show this work by Linda Tacconi, where they have a lot of molecular gas for main sequence galaxies, and they start to recover different patterns or scaling relations for the galaxies. So for example, here we can see that in this axis, we have the stellar mass, and here we have the gas fraction, for example. And we can see that there is a relation of the gas fraction with stellar mass. The most massive galaxies have less relative gas than the less massive galaxies. And as you can see here, if you go below 10 to the 10 in stellar mass, there is not so many detections or information. So here we really don't know what is happening, at least at high redshift, at cosmic noon. And the reason for that is that it is difficult to detect the molecular gas in fainter and less massive galaxies, because if you go further, they're gonna appear fainter on the sky, so it's difficult. You need more time to detect the molecular gas. And this can be reflected in this plot where I'm showing the redshift for this sample of galaxies, and what are the measurements for the stellar mass. So above redshift 2, you are just recovering the high end of the mass range. So this is, for example, to the right, I'm showing you a GN20, a very massive galaxy that I like it because it shows that we, at least for the massive end of the galaxies, we can learn a lot about the distribution of the different components. For example, this is a submillimeter galaxy. It was detected in the submillimeter. And you can see that in blue, we can see the HST observations, which is just showing the rest frame UV. But if you go to the molecular gas and the dust, it's all located in the center. And now that we have NIRCam and NIRI, we can recover the older population of the galaxy, and we can get a real size, or to get all the global information about the galaxy. So this is something that we can do for these massive galaxies, that they are bright in the different bands, but it's harder if you go to the lower mass end. And how do we do it then? Do we spend 50 hours per galaxy and get the information? Or we use gravitational lensing? So as you may know, the gravitational lensing is when you have a very massive and compact object in the middle path of your source, and us, the observers, and because of the bending of the light, this compact object is gonna magnify the light that we're receiving from the background source. And this is something that has been used in the optical and in the far infrared and in the submillimeter for many years. It's nice because you get the sources appear brighter on the sky, and also they appear more extended, more elongated. So for example, here I'm showing you SDP 81, which is the poster child of this kind of observations for ALMA, at least, because it's a really bright submillimeter galaxy where you have close to a full Einstein ring And this source has been explored in many lines, in different bands, in continuum, in C2, in CO, high JCO, for example. So we know a lot of the information. We know a lot for this galaxy because it's really bright and you can get a lot of information from the different tracers. But there is a problem: is that if you observe this ring, this is not how the galaxy really look. You need to know or try to estimate what is the properties of the lens, in this case, a single galaxy or a galaxy cluster, to recover what is the real distribution of the galaxy that is behind the lens. And this is something that we can do. And actually, for example, this is the source plane reconstruction. What would be the real distribution of the different tracers for this galaxy? We can see that the far infrared, for example, the dust continuum is more compact than the CO, and the CO is more compact than the C+ emission, for example. And we can go to the different positions and get information. And for this, we really need the information of the lens. We need to have very good lens models to understand what is happening. So this is the tricky part of studying these strongly lensed galaxies, that you get more photons, you get brighter objects, but you need to take into account that your model can be very good or can be very bad. And that's something that you need to be aware when you're doing this kind of observations. So we have gravitational lensing, and we were hoping to use it as a tool to study these more normal galaxies that contain none. And this is something that we started several years ago. This was in 2017 that we published this paper, where we targeted this beautiful arc on the left. This is RCS 0327. It's a galaxy, it's a strongly lensed galaxy at redshift 1.7, and it's being lensed by a galaxy cluster that I don't remember the redshift. It should be something 0.4, 0.5. And what is interesting about this arc is that it was discovered in Sloan. And at the moment of writing the proposal and publishing the paper, this was the brightest gravitational arc in the optical bands. So it was a good target to start to explore the molecular gas and the dust content in this kind of objects. Because, for example, for the other source that I showed, the SDP81, that source was detected in a 2 millimeter survey. So people knew that it was very dusty and very massive with a lot of stuff formation. But in this case, we only see the UV emission for this galaxy. So we really don't know what is the dust content or the molecular gas content for this galaxy. And it's important because at the end, this galaxy was cataloged as an LPG galaxy, a typical low metallicity galaxy at cosmic noon, but we really needed the other components of the molecular gas and the dust content to really have full property of the galaxy. And this is what we did. We went with ALMA and we detected different zero transitions, for example, the dust continuum in the different bands. And we were able, thanks to a good lensing model that we had for this galaxy, we were able to take this information and go into the source plane, for example. So here on the left, I'm showing you the source plane reconstruction of this strongly lensed galaxy. In blue is what we see in HST. So the galaxy, it has this shape in the source plane. And in red, I'm showing you the molecular gas. And in green, we have the dust content. So this was the pilot program to really push forward the idea of using these optically selected gravitational arcs bright in the optical bands to explore this parameter space in molecular gas and the gas content for these galaxies. So we were able to put in context what was happening with this galaxy. For example, if we compare the molecular gas and star formation activity for this galaxy, and you compare it with the local analogs, this galaxy is very similar to the blue compact dwarfs, which are galaxies with not so much gas, but with a lot of star formation activity. So they are very efficient in forming stars. And the same is happening here. So we were able for this galaxy to put the context to really understand what's happening, at least in this region of the galaxy. But more importantly, for example, we were able to resolve the CO excitation for this galaxy because we had different CO transitions, and we we were able to get, for example, in here, I'm showing you different apertures where they have the ratio between the CO6 to 5 and CO3 to 2. This is only to show that actually the CO excitation is higher, is closer to the UV bright clamps where the star formation activity is happening. And this is what you expect, that in this region, you will have the gas that is much closer to the newly formed stars, and it's going to get denser and hotter, and that's why you expect a higher CO excitations, for example. So this is something that we did many years ago, but motivated by this, that we could do it, we started a program to expand the sample. So we had the first arc that was the brightest in the optical, and then we follow up the three other bright arcs that we had access at the moment. So here I'm showing you three different arcs. Here, for example, this is one that was discovered in a galaxy cluster that was discovered within the Planck mission. So this is the sunburst arc. That nowadays, this is the brightest optically selected gravitational arc that we know. For example, previously it was the other one that we were studying. And for these arcs, we use an ACA project. So we use the compact array of ALMA to try to get the molecular gas, the dust content for these galaxies. And for that, we wanted to detect the lowest CO transition that we had access, and C1 for those redshifts where we could tune CO and C1, and also the dust continuum in band 7, just to have an alternative way to get the molecular gas and the dust content. So first, and I'm showing you here that for some of the arcs, at least for this one that's really bright in the optical, we didn't detect continuum nor any CO lines. But for the other ones, we detected the continuum and the CO, for example. So we had a good success rate for these three galaxies, and we were able to get the properties in general for the global galaxy. And something that I want to mention here is that ACA, one of the characteristics is that the beam size, the synthesized beam, is really large. For example, at low frequencies of 100 gigahertz, you can get a beam size that is, I don't remember the exact value, but it's close to 10 arc seconds. So it's really good if you want to detect these extended sources on the sky. So this was the perfect machine to use this kind of discovery projects for these extended sources. So, for example, for this galaxy, we recovered that there were not so much obscure star formation. So what we see in the optical bands is most of the star formation. And again, this galaxy, the four systems that we had in the first program, they are consistent with being main sequence galaxies at cosmic noon. But what is important here that I'm showing you in the green cloud, this is the Tacony sample of main sequence galaxies at cosmic noon. And this is the mass range. And in blue, we're showing you all the CO studies that have been done in the local universe. And as you can see, because of the magnification, we're exploring this parameter space that is really hard to do at high redshift. And in the yellow triangles show other strongly lensed galaxies that have been explored with ALMA, for example, or other interferometers. So this is the only way that we have to explore this regime in the main sequence without going for hundreds of hours with ALMA. So we confirm, first of all, we confirmed that these galaxies were main sequence galaxies. They were not very massive or very active. But more importantly is that using the CO detections and the upper limits and the continuum detections, we were able to get the molecular gas for these galaxies. And we got, for example, here, the gas fraction, the molecular gas fraction, and the depletion time for this galaxy. And as you can see here, we have the main sequence at redshift 2, and these lines show the different extrapolations of the scaling relations for this galaxy. So as I showed you many slides ago, if you go to a lower stellar mass, the gas fraction increases. But what we're seeing here is that in this mass range, the gas fraction is really low. So we have that there is a deficit, a potential deficit in molecular gas for these galaxies. So these galaxies, they don't have as much as molecular gas as you would expect, given the extrapolations of these scaling relations. And they have even lower gas fraction than the main sequence galaxies, that more massive ones. And at the same time, here we have the depletion time. So they don't have a lot of molecular gas, and they still have a lot of star formation activity. So if we assume that no further gas is going to fall into these galaxies, the depletion time for these galaxies is very short. Actually, it's in the low end for the depletion times of all the main sequence galaxies that were presented by Tacconi et al. So this is where we have main sequence galaxies that they have at least some characteristics that are consistent with being starbursts, for example. These are very short depletion times. So you may ask, can we trust these results, for example? Are we making some assumptions that are wrong for these galaxies? That's one option. So do we have a molecular gas deficit in these galaxies? So we explored different possibilities. For example, we checked that the stellar mass and the star formation rate that we were estimated for these galaxies was consistent with other studies and other teams that were studying the same galaxies. So it's very unlikely that we are just getting the wrong estimates for these properties. So there is another option, and actually we could be affected by differential magnification. So this is something that different regions of the galaxies can have different magnification values. So it could be that actually the star formation rate tracer, for example, and the UV clamps, they are closer to the caustics in the source plane, and they have a higher magnification than the molecular gas that could be more extended, for example. This is something that can happen, and it's really difficult to test if we have the situation, but actually it's very unlikely that we have the same differential magnification happening in the three systems that we have. So it is a possibility. We should explore more galaxies in the future just to check that we are not affected by this issue of the differential magnification. So, but at least for these 3 or 4 galaxies that we were exploring in this project, it shouldn't be a major issue. But the final important part is that all these galaxies have between 10 to 50% solar metallicity in the gas, measured with deep optical and near infrared spectroscopy. So, and for the low metallicity population of galaxies, we know that all the different conversion factors that we use to transform the CO luminosity, the dust mass, and the C1 luminosity to molecular gas can be affected by the metallicity, because we know that, well, people have been known for many years that actually CO is a good tracer for the molecular gas at solar metallicity. But if you go to a galaxy or a region with a low metallicity, the photons from the young stars are going to dissociate the CO molecule, and therefore CO is not going to be a good tracer of the molecular gas. So your alpha CO will be much higher than the typically assumed, for example. And this type of galaxies, actually, what they propose actually in this paper is that for this kind of galaxies, it could happen that actually the C2 line from the C plus element, it would be a better tracer for molecular gas than CO. But we were aware of this, and we tried to use all the latest recipes to try to estimate what is the proper alpha CO value for our galaxies according to the metallicity. And okay, we have a range because different recipes give different values, at least in the low end of the metallicity range, because close to solar, they all kind of agree. You have something between 4 and 10 in this range, for example, here. But if you go to really low metallicity, we really don't know what is the alpha CO for this system, because it could be 50, 100, 500, we really don't know. But if you take into account all these different recipes, we can actually get the different molecular gas estimate using the different observation that we had. And at least, for example, for this galaxy, that we have CO, we have atomic carbon, we have continuum, and all of them agree within a factor of 2 or 3. So even though we have these large error bars associated with the different tracers, all of them kind of agree that in the same value. And just to show you that metallicity is something important in these cases, but we think that we are making a good job trying to estimate the molecular gas in this system. So with this information, and I hope that you believe me that we are trying to get a good estimate of the molecular gas, we can go, what is the conclusion of this? Are these galaxies really efficient in forming stars with the low amount of gas that they have? Or something is happening with the gas? For example, are we just catching these galaxies when they are being affected by feedback, for example, and the gas, and the molecular gas, more importantly, is being removed from the galaxy? These are the important questions that we have for these galaxies. Why they appear to be main sequence galaxies with these starburst-like properties based on the gas, low gas fraction and short division times or a high formation efficiency. So we have two options to study further this question or these galaxies. First, we can go into the details of each specific galaxy and try to get more information, more complementary information to understand the property, and actually expand the sample of arcs that we have been observing to maybe check if these 3 galaxies that we detected in the beginning were just special cases and they are not a good representative. They are not representative of the general population of less massive galaxies of cosmic noon. So first, I'm going to show you what we have been trying to do to study these galaxies in details. And for this, we need to go to other wavelengths to get different phases and different components of the galaxies. So I'm going to focus first on this galaxy, which is one that was detected in dust continuum with the ACA observations. So this is SGAS 1226. This is the galaxy A, and this is the galaxy B. These are the 2 arcs. And here we have something that is the same color as these galaxies. And actually, this is another image, another lens image that corresponds to the same galaxy as this. So this is galaxy A, this is another view of the same galaxy A, and this is galaxy B. And this is a foreground galaxy that is a redshift 0.8. And these 2 blue galaxies, they are redshift 2.9. So for example, what you can do with this galaxy is to use the lights from these higher redshift galaxies as background sources and study the CGM for this foreground galaxy in absorption in these arcs. So this is what we are doing that we call arc tomography, that is used this gravitationally lens galaxies to study the CGM of these foreground galaxies. And to do this, you need MUSE data. MUSE is the IFU spectrograph that is available at VLT, at one of the UTs. And what is nice is that you get an spectra in each different spaxel. For example, we can get a spectrum all over this field, and we can use this information to study the CGM of this galaxy at redshift 0.8. So me and the students, we collaborate within the arc tomography, and they focus on this lower redshift galaxy. And we use that information to study the background sources, which are the ones that are interesting for us. So using this MUSE data, we were able to discover that actually there is this huge extended Lyman alpha emission that is coming from the redshift of these 2 galaxies at redshift 2.9. So as you can see, we have the UV emission as seen by HST, and this is the whole extension of the Lyman alpha emission surrounding all the different images for the galaxy. Like here you can see that actually this is one view of the galaxy, this is the other, and here they are connected by Lyman alpha. And also we see that there is kind of a bridge to another source here that is detecting the Lyman alpha. This is just to show you that at least with these instruments and these special galaxies, we can get a lot of information and try to understand what is happening, for example, in the CGM of these galaxies, in the gas nearby the galaxies. And this is something that we did. And with the lensing model, we were able to take this beautiful extended Lyman alpha nebula into a source plane and compare it with the distribution that you see in HST, for example. So here I have the source plane reconstruction for galaxy A and the source plane reconstruction for galaxy B. And in the background, we have the Lyman alpha nebula as we would see it in the source plane. And what is nice, because we had such a high signal to noise, we were able to create different beams and explore the Lyman alpha profile in the different beams. And with the Lyman alpha profile, you can model it and try to get different properties of the neutral gas that is being excited and is shining in Lyman alpha. And this is what we did here. We went to the different beams and we got the different properties for the Lyman alpha emission. And if we assume that the typical expanding shell model for Lyman alpha is valid for these beams, and actually the models are very good. We can model all of the profiles with this expanding shell. We recover that you need an expansion velocity that is kind of consistent across the whole region and is lower, closer to the galaxies, and is higher farther from the galaxies. And we also got the column density for the neutral hydrogen, and with the same information, we were able to get the systemic redshift for the gas that is shining in Lyman alpha. So what we think that is happening here is that we have that these two interacting galaxies, they are at the same redshift and they are separated by a few kilometers per second. They are producing this extended Lyman alpha nebula because of the interaction, but also because of a possible outflow that is expelling gas from the different galaxies. And actually, that outflow is consistent with the star formation rate that we are able to recover for these two galaxies. So, at least for this system, where we measure the molecular gas using the ALMA observations, and we see the deficit, we have some hints that there is an outflow happening, and that could be, for example, expelling the gas in this galaxy or preventing the formation of the cooling of the molecular gas. And in an alternative way, we knew that this galaxy was special because in the UV, it was very compact. In Lyman alpha, it was very extended. And we wanted to check how this galaxy would look in the C2 line, the line that is tracing the C+. And this is what we got with the ALMA observations of C+. And as you can see, it's not as extended as the Lyman alpha, but it is more extended than the UV. And also there are some regions that you have a lot of C+ emission where you don't see UV emission. And actually, we think that the dust continuum here, there is a really obscure region here where it's really bright in C+. And so we're using now the C+ line to try to get a complementary view of this system. We detect C+ in the B galaxy and in the A galaxy, but now we have this tail of C+ that is appearing is co-spatial with the galaxy redshift 0.8. So this is not coming from this galaxy, and actually this is a cloud that it should be in the system at redshift 2.9. But we were not able to pinpoint really that there was a different cloud in Lyman alpha. Well, Lyman alpha is all over the place, but this is a C+ emitting region that is closer to this galaxy A, and maybe is in the middle of the two galaxies. So what is important that what we can do with the C+ emission is to, for example, test if we were getting a good estimate of the molecular gas. So we use the C+ luminosity to estimate a molecular gas value, and it was really consistent with the previous measurements. So at least in this galaxy, we support the previous values that we measured, and we really don't think that the metallicity is making a huge impact in the estimate for the molecular gas in this galaxy. What is more important that you may ask about the C+ emission is that we get information that was not available in the news data. because now, for example, we can get the kinematics of the two galaxies. And we can use, for example, this information to improve the lensing model in this case, because the galaxy A is really well constrained by the model, because you have different clamps that appear in different regions, and you use this information to constrain the model. But here we don't have other images of the same galaxy. So now with this information, with the kinematics, we can, for example, try to assume, is this galaxy, or test maybe is a better word, is this region of the galaxy the same region as this one, because they share the same velocity. And some models that we have also suggest that these are two views of the same region of the system. So now with this information, we're trying to improve the model and get more information and try to recover a better source plane reconstruction for this galaxy. And also here, I just want to show you that we have a gradient in velocity that could be a rotating disk or a merger system that we are detecting here. And we can use this information to further improve our understanding of these two galaxies at cosmic noon. And finally, because we have been trying to push really forward the study of this galaxy, it was nice to see that this galaxy in particular was selected as one of the early release science James Webb programs, where they targeted the ARC-A with near-spec IFU to get more information and to try to go into high spatial resolution with James Webb and to test the instruments. And also they observed the whole field with NIRCam, with all the NIRCam bands. And we were able to use that information to get a better estimate of the stellar mass and stellar formation rate. But what is more important is that at the moment that they wrote that proposal, they focused on the galaxy A. But now we really think that galaxy B is way more interesting. It's brighter, you have more dust, more molecular gas, and we really think that this is more active than the galaxy A. So we proposed with Manuel Solimano, my student, to do a near-spec IFU mosaic in the galaxy B and try to compare the properties and try, for example, to see if this potential outflow that we see in Lyman alpha is also seen in H alpha. And at the moment, Manuel is trying to study this galaxy, galaxy A, and prepare for when we receive the data for galaxy B, and maybe hopefully see if H alpha is as extended as the Lyman alpha, or is as compact as the UV and the C+ emissions. So this is going to be a really important project for us to try to understand what is happening with these low metallicity galaxies at cosmic noon. So this is all that we have been doing for one of the arcs that we explore in this ACA program. But we have another one, which is the S-gas 0033, that we, with the ACA observations, we detected CO322 with high signal to noise. We detected continuum in different galaxies. So it was a good target to go for higher angular resolutions. And this is what so just to show you, this is the arc that it has an extension of close to 15 arc seconds. This is the synthesized beam from ACA. It's really large. And this is what we recover with a 0.2 arc second beam in the arc. So we have the CO322, it's really extended, it's following the same extension as the UV, it's more extended than the UV actually. And just here we have, I'm showing you that we have a profile that is better fit by two Gaussians, which is it could be a signature of an outflow. We have also a clumpy CO emission. We are trying to use all this information to try to understand what is happening in this galaxy. And what is nice is that people have been trying to study this galaxy for years, and there is HST, as I was showing, but there is also symphony observations with adaptive optics with the same 0.2 PSF. So actually we can trace this galaxy in different components and try to understand what is happening. For example, we can use the H alpha to estimate the star formation activity. We can use the CO to get the molecular gas. We can use the HST band, some of the redder HT bands to get an estimate of the stellar mass, and we can compare what are the, for example, the profile for the different components. And here I'm showing you that the CO, for example, is more compact in the center than the star formation activity. So this is just to show you that here the star formation efficiency is higher in the outskirts of the galaxy and is lower closer to the center. So maybe this is a signature that there is a feedback process that is preventing the star formation activity happening in the center of the galaxy, and we're just exploring what is happening in this case. And also with these higher angular resolution observations, we can go and resolve the gas and the star formation activity and compare with other galaxies. That this is something that typically that you do when you have resolved gas tracers. So I'm just going to show you what I had been working with this data for the last year, where here I'm showing you, and Tanya is really gonna like this plot, because this is the moment 0, the moment 8, the moment 1, and the moment 2 of the CO line. And as you can see, it's really well extended, the CO emission. But I see if you go to the moment 8, which shows the peak of the emission in a given spaxel, you have that this bright region could be the same as this bright region. And if you go to the velocity field, you have an excess at close to 40 kilometers per second, and you see the same excess here in the opposite side of the arc. And you have the same in the dispersion. And what I'm trying to say here is that it is clear that here we are seeing two different views of the same part of the galaxy. So we have that this, at least this point to the top is one view, and from here to the bottom is a different flipped view of the same part of the galaxy. So this is really important to understand what is happening with the lensing model, to try to understand what is happening in the image plane, which is what we're seeing here. And I'm going to go further into the lensing model in the next slides. So, but what was the main test that we did for this galaxy? If we could see an outflow, for example, because with the Symphony data, they saw that all the ionized gas tracer, the H alpha, the O3 lines, they had these broad components. For example, here you can see that there is a narrow component and a broader component. And they did the reconstruction in a paper a couple of years ago, and they measured that actually the broad component is 700 kilometers per second. This is the width of the broad component, which is consistent with having an outflow and maybe an EGN. So what they found is that it's very likely that there is an EGN in a region of the arc. So motivated by this, we went to the molecular gas, to the CO emission, and we tried to look for a broader component and a narrow component. And actually, when you take the whole emission line, and you test if you get what is the best model that you get with one Gaussian and with two Gaussian, we see that actually the better model is when you have the two Gaussians and you have a broader component that is not as broad as the one seen in the ionized gas, but it's still broader than the narrower. So the narrower it has a full width, has maximum of close to 80 kilometers per second, and the broader it has a 130 kilometers per second for the full width hat maximum. It's not much. It's really at the same order of the narrow, but it's still telling us that maybe there is a potential molecular gas outflow in this galaxy. But more importantly, we have a hint that there is possibly this extension in the gas. But thanks that we have this high angular resolution observations, we try to recover if we can pinpoint where this potential molecular outflow is happening. So here I'm showing you in green, these are the different apertures where I did the same test of recovering one Gaussian or two Gaussians. And the blue crosses show all the apertures where the two Gaussian is a better fit than the single Gaussian, taking all the different tests to check if one model is better than the other. And we recovered that actually we have potential broad component here and here in this region of the arc. And this region is co-spatial with the potential outflow that was measured in Symphony. So this is consistent with the idea of having an AGN that is being pushing the gas outward in the galaxy and is preventing also star formation activity close to the AGN. It could happen. But what is important is that we have this other region that is also in agreement with the idea of having a molecular outflow. But we need to check if this is consistent with the lensing model, for example. It could be that these two regions are those two images of the same AGN that we're seeing, but in that case, it is not easy to explain why it's so extended compared to the region with the molecular outflow on the top. So here I was just going to show you that we can actually try to recover what are the properties of the narrow and the broad component and try to see if we can get a movement of the broad component or if there is a relation with the spatial. But at the end, there is some hints that in some different regions, the broader component is way more important than the others. But but before going into explaining the molecular outflow, we wanted to test if maybe there was a second component, a second kinematic component that was also creating this broader and slightly higher velocity in the galaxy. So we checked if actually the outflow could be just clamps that we are seeing, because this is the position velocity for the CO line across the arc. And you can already see that there are these clamps that actually could be start forming regions that they have different velocities, and they are producing these potential molecular observations of component. So we use dendrograms to try to recover these structures within the more extended CO line, and we check that in fact we have clamps. We recover all these clamps, but all of them have velocities closer to zero, and they are not the ones that are causing this higher velocity emission. So we think that there are some clampy regions in the galaxy, but the outflow actually is something that is more associated to these longer, higher velocities here. So we have clamps, but they are not the ones that they are causing the broader and higher velocity tail for the CO line. But now, this is important now that we have clamps, we can use these clamps to try to go into further analysis in this galaxy. And we can see, for example, that at least here we have a clear clamp with no counterpart in the UV, which is interesting. This implies that if there is a transformation activity here, it's really obscured by dust. But we also have other clamps that they are really on top of these UV bright clamps. So for example, this is the position of where the potential AGN is located. So it's really important to see at least a CO clamp of molecular gas around this part of the galaxy. And we have a lot of clamps. We have close to 20 clamps in this data cube. But more importantly, we resolve these clamps. So this is something that I'm trying to do now, is to get the properties for these clamps. We can try to get the dynamical gas for these clamps, and we can compare it with the CO luminosity and try to make a measurement of the alpha CO, for example. And this is something that we can do, and we have been trying to do. Also do science with these clamps that we are detecting in this system. But more importantly, we try, because we detected these clamps in the CO, we also try to look for clamps in the dust continuum emission. So here on the left, I have the dust continuum detected in band 4 at 2.2 millimeter in the observed frame. And here is what is detected in the band 7 at the 850 microns. And as you can see, it looked really clampy. We know that actually the ALMA data, the interferometric data with low signal to noise can create these clamps in this low signal to noise detection. But what is important is that several of these clamps, they just fall on top of the UV bright clamps, for example. Here we have one, here we have one. We have that some clamps, they are co-spatial with other clamps in different bands. So we really think that these clamps or this clampiness for this emission is real. They're tracing real structure in the galaxy. and we need to understand why do we have these clamps in the continuum, and more importantly, why we have clamps that we see at 2.2 millimeters and we don't see them in the 850 microns, because at the end, the 2.2 millimeters is only a fainter, a less luminous view of the same dust that it should be visible in band 7. So this is important because actually, if we test, we compare if this dust emission is consistent with just being emission from the cold dust in this galaxy, we get that if we add up all the emission in the arc, we get a potential SED, dust SED that is consistent with what is expected. We have no information about the temperature for the dust, but we can recover a typical spectral index for the dust of 2.4, which is not crazy. But if you go into the very center, close to the potential location of the AGN, and if you assume that this is only producing by a point source, you get something, a beta value that is 0.8. So it's really low to explain the dust emission. This is only to show you that actually it could be that we are seeing some synchrotron emission from the AGN. And that also could explain that we're seeing these offsets between the band 4 and the band 7 data. This is the 2 millimeter clamp. This is the 2 millimeter clamp that is actually between two band 7 clamps. So we have the potential of maybe having the detections of an AGN. And this is, again, work that we're trying to do. And I'm just going to skip all the studies that we're doing with the clamps to actually improve the lensing model, because there are two models available for this galaxy, for this system, and one of them is more complex and it better fits the data. And what is important is that when you do the source plane reconstruction of the different clamps that we see in the different tracers, for example, we see that in the 2.2 millimeter clamps, if you take them into the source plane, they fall into different positions in the source plane. So actually, it could be that we are seeing different regions in the band 4 data. But if I go to the band 7, I can show you that, for example, we have two independent clamps. The two on the extremes of the galaxy, they fall into the same position in the source plane. So we have one model that is actually is able to recover the positions of these clamps, and we know that they are the same region in the galaxy. And something similar is happening with the other clamps. So this is only to show you that we are trying to push forward into the understanding what is happening in these galaxies, and we have some hints that there are some potential outflows in the galaxy that we detected this gas deficit. But now we want to expand the sample to confirm the previous trends that we saw. And what we did, we pushed for a program to do the same experiment with the ACA, the ALMA compact array, and now detect the CO and the dust emission in these other 6 bright arcs that have been discovered in Sloan. And we were lucky, and we have some detections. We have some detections of the CO and continuum in different arcs. And now I think that we have 11 or 12 systems where we have CO and dust emission observations. And we can try to see if they still appear as galaxies with a gas deficit. And more importantly, now we have the ability to do a stacking, because we have a really good measurement of the systemic velocities for this arc, and we can stack all the CO lines that we could measure for this galaxy. For example, here we have the result for the stacking of all the sources. We have a clear detection, but it is dominated by one of the galaxies. But even if you remove the individual detections, you can see that there is still some emission. So if we do the stacking of this galaxy and we create this pseudo reference for galaxies at the cosmic noon and they have low metallicity, we have this estimate for the molecular gas for these stacked galaxies, which are the blue points here. So here I'm just showing you what we have for the combination of all the different galaxies. And again, all of them are consistent with being main sequence galaxy. Although it's kind of interesting that all of them are below the main sequence at redshift 2. They are kind of, there is a trend that they are going into this direction of the main sequence. And again, in the gas fraction and in the depletion times, we recover the same trend as before. For some of the galaxies, the upper limits are not as constraining as we would like. We're asking for more information to maybe see if there is a potential detection here. But in general, all the galaxies that we have observed and we have detected the CO line, they have what a potential molecular gas deficit. So here, the stacking is really below the scaling relation for the other main sequence galaxies in the more massive end. So we really think that we have these galaxies that appear to be main sequence galaxies, and they have small amounts of molecular gas and high star formation rate, high star formation activity. So what's happening here? We have these different proposals that maybe they're very efficient or they are just expelling the gas. And I just want to finish with mentioning that this is not the first time that we have this kind of objects at cosmic noon, because there was a paper last year that they were doing a similar study in the more massive end, 10 to the 11, for example, solar masses in a stellar mass. And they also recovered that the gas was low compared with other sources. So they had, they were main sequence galaxies, but they had starburst-like properties. And what they propose actually is that it could be that at least for this massive end, they are catching the galaxies just in the process of having the last starburst phase before they leave the main sequence and they become quiescent galaxies. So this is the different scenarios that they have for this massive end. And we really want to explore if something similar is happening for our lower mass galaxies, or is a totally different process. Maybe it could be that we are just witnessing these really efficient galaxies that they are just waiting to accrete more gas to continue and grow and form more massive galaxies in the local universe. So I'm going to leave you with the summary because I'm running out of time. So thank you.
Okay, thank you very much for the very nice talk. Let's see if we have some questions from the audience. Any? If not, I have a couple just to.
Good.
So I think it was the first of the S-gas.
The 1226.
That in which you detect this one. Actually, the second, yes.
Which, sorry.
Where you see that there may be an outflow.
In this one?
Yes, the one that you separate into components, and also you see the outflow. I think in H alpha as well. This here, this. Yeah. I mean, I noticed that the normally when you see outflows, they tend to be, blue shifted, not red shifted, right? So yeah, this is a very particular configuration that you should have in order to see this red shifted outflowing material, no? So
yes, that was also a question that we had, and someone said that it could be actually that you have that these emission lines in the optical, they are something that is obscuring the red part of the line, and we're only seeing the blue part, and that's why it's blue shifted in the optical lines. But the CO line should be optically thin, and you should see the whole component of the line. That was one of the explanations that we saw in the literature, because this is something that has been detected before in some sources, but the explanation is not clear to me yet what is happening.
Because
but it could be that.
And especially at these very low velocities and low full width of max, small width of max, you cannot rule out that, especially if you see something redshifted, that may be an inflow rather than an outflow, right?
Yes. I can say that there is a second broader component in this galaxy that is located in specific regions where you also see the broad components in the optical lines. But can I be sure that it's an outflow? No, it could be gas going in the different direction, for example. And that's something that, as far as I know, is really difficult to really be sure that it's the gas outflowing of the galaxy. It could be consistent with a low velocity outflow.
Okay.
But I cannot claim that it's a molecular outflow.
Okay. And the other question I had was when you compare these low mass cosmic noon galaxies in the context of the main sequence, right? Like when you show star formation rate as a function of stellar mass at the very end. You compare it with normal star formation, more massive galaxies at cosmic noon, and also low redshift gas-rich galaxies, no, from the X-Cool cool gas survey. But you also say that in your sources are kind of lower metallicity as well, right?
Yes.
So maybe a more interesting comparison would be to also plot in this, where would low metallicity galaxies in the local universe would be here, right? Are they also below the purple contours at redshift 0, or would follow also?
Yeah. Actually, I haven't explored if you get different main sequences for different metallicity galaxies in the local universe. Yeah.
Because I assume that extension of the purple contours towards the low mass values, they still do not, still do not enter into the low metallicity category at low redshift, right? Because at low redshift, the low metallicity galaxies have stellar masses of 10 to the 8, right? Or something like that. So I think that would be interesting because there are, I don't know how that comparison would look like.
Yes. So, okay, this is in the typical properties that you get. Now that you mention it, would be good to do the same experiment or comparison with the molecular gas in this lower galaxy because low metallicity.
We know they are low metallicity galaxies and low redshift also lack CO, right? But it's the amount of how much they lack may be different.
And as I told you in the beginning, for the first system, we recovered properties that they were very similar to the blue compact dwarfs, which are the local galaxies with low gas content, and they have similar properties.
Okay.
Thanks.
Anyone else with questions? Extragalactic, especially extragalactic researchers? No takers.
No takers.
no takers today. It's in the afternoon, so it's 5 people.
People want to go home.
Today. Okay, so if there is no questions, we can wrap it up. And well, if you think about it and you have some question from here to June, Jorge will visit us.
Yes, I will go.
in for the conference that we are organizing here in Crete in June. So by then, if you have any question, you can ask him in person.
Good.
Okay, so let's stop the recording.